right, I'd like to thank everyone for coming out tonight. Yes. If I could have your attention, a couple of quick announcements. For those of you taking the class for credit, and that's the people who are signing in the top, so 494. I wanted to make two announcements for the 494 class. One of which, and well, actually this goes for everyone. Everyone should know that next week there is no official What Physicists Do. We pick up on March 9th. For the people enrolled in the class and for any physics majors, I will be having a student seminar discussion of career advising, so things about statements of purpose and cover letters. So let me say that again. If you're taking this as a class for 494, I expect you to be here next week. I have a link up to some materials you can take a look at for advising and thoughts and careers in physics. Some of you who are taking 494 are not physics majors, though most of you are. And during next week, we'll talk about things that are applicable to non-physics majors as well, but with a physics major bent. Also, for the 494 students, you should take a look at your feedback from the first two assignments. So those are both up, and I'd like you to have a chance to look at that, and then make note of it, and however you use that in your assignments moving forward. So thank you. So as a group as a whole, we will not have What Physicists Do next week. It's a special thing for students, and we'll pick up again on March 9th. That's on the web calendar. It hasn't changed on the web. Well, I'm really pleased to introduce today Dr. Jim Gaffney of Lawrence Livermore National Lab. He has a PhD in plasma physics, although we were talking about mostly atomic physics, or at least a good part atomic physics, from Imperial College in London, and his prior work and his Masters of Science in physics was from the University of Durham. He joined Lawrence Livermore National Lab as a postdoc in 2011, where he is now a staff physicist. He's working on the National Ignition Facility, which he's going to be talking about today. Let's give a warm welcome to Dr. Jim Gaffney.
Okay, thanks. Thanks for that great introduction, and thank you to everyone for the invite. I'm very excited to be here talking about ongoing experiments at the National Ignition Facility, which is in Livermore, California, just down the road. In those experiments, we're attempting to ignite hydrogen fusion reactions in order to generate more energy than we have to put into the experiment. The idea is that we'll one day be able to use that to generate electrical power. That has been considered to be one of the greatest challenges facing mankind for several decades, but we're still not managing it. And I'm going to tell you a little bit about why and the work that's going on at my lab to try and figure out what we can do to solve the problem. Our experiments are using this building here, which is called the National Ignition Facility. We call it the NIF, which means I don't fall over the words every time I say it. So that is, although it looks like a building, it is in fact the largest and most energetic laser system ever built. In a single shot, its peak power is about 500 terawatts, which probably doesn't mean much to some of you, but I'll tell you that's 1,000 times more than the power consumption of the USA. And it delivers that power in about 10 nanoseconds. And all of that is focused towards imploding capsules of hydrogen to conditions where nuclear fusion reactions will take place. So why are we bothering? I'm going to let Stephen Hawking explain. So he said it would provide an inexhaustible supply of energy without pollution or global warming. So while inexhaustible is a slight exaggeration, it's not far off. The fuel for the reactions that we propose comes from seawater. They're isotopes of hydrogen. It's been estimated that our current power usage, the sea contains about 10,000 years worth of fuel for these fusion reactions. The reaction takes those hydrogen isotopes and fuses them together to generate helium. So, and helium is of course inert, so there's almost no environmental impact associated with that reaction. Add to that, as opposed to nuclear fission reactions, fusion is inherently safe. The reactors that we propose contain so little fuel that even if you were to lose control of the reaction, it would never escape the reaction chamber. So you would never get one of these meltdown situations that are so famously dangerous. Alongside that, governments like it because there's no exotic materials involved. You can't. The reactor isn't spitting out stuff that you could then use to make a bomb out of, and so it's very secure and it's a win in every way. That's why I say it's one of the greatest challenges, but certainly worth the effort. But it's also very difficult, and you can understand why from a fairly straightforward cartoon. So the fundamental reaction is you're going to take two nuclei and you're going to jam together. They're going to fuse together into one nuclei, and you'll get a lot of energy out. And you're going to capture that energy and harness it to make electricity or whatever you want to do. And of course, this is the problem. You've got two nuclei, they're positively charged. In order to bring them together, you have to work against their mutual repulsion. It turns out that electrostatic force is really strong. That's a lot of energy required to push those nuclei together. And so, in order to, if you want to envisage a situation where you have a large amount of hydrogen producing a large amount of energy, that means there has to be a lot of energy there to overcome the repulsion sufficiently fast. On Earth, that large amount of energy would then have to be surrounded by ambient conditions, probably a vacuum. And so there's a very large energy gradient there, and nature won't let you have that situation. And so regardless of the approach that you're trying to use to get to fusion conditions, nature will find a way to even out your energy gradients in the form of an instability, which will mean you no longer confine your plasma, and you lose all your energy before you manage to make fusion. Of course, we think we can overcome all those problems, and that's because we have this thing, which is in fact a laser. It's 3 football fields big, 192 laser beams, all focused on 1.1 millimeter across. I don't quite know. I think this is the target chamber there, and this is the laser. I'm not really sure. This is a really exciting experiment, and it's the closest that we've ever been to managing to do this, because the technology is so good. And in this talk, I'm going to show you some of the really amazing things that this laser is able to do, and I'll walk you through some of the physics problems that we've discovered already. Now, of course, what's so emotive about the fusion reaction as a way of generating energy is that it happens in nature. Fusion is what powers stars, and so indirectly that's where all of the energy on the Earth comes from. So how is it possible to happen in a star, and why is it so difficult for us? Well, that's partly because of the way that stars are formed. This is a completely gratuitous slide, but I wanted to put it on because the Hubble Space Telescope has started revisiting their most favourite targets and doing pictures in high definition, and they're coming out amazing. So I thought, well, great, I'll stick some pictures in because I can. So these are 2 star-forming regions. They're both nebulae, big gas clouds, and if you look at these closely, you'll find that there's a very high density of young stars, and the interpretation is that stars are being born out of the gas in these nebula. What actually happens is that small clumps form in the gas, and they attract more material, and eventually there's kind of a gravitational collapse of the material and that forms a star. As that happens, the material heats up and the density increases to the point where you get to the conditions where fusion can occur. And in most hydrogen burning stars, that happens via a reaction called a PP chain. It's a chain of 3 reactions that essentially takes protons, that's hydrogen nuclei, and burns them into alpha particles, helium. So that's the reaction we want to do. And the reason stars are able to do it is that the conditions at the core of the star are so extreme. So let's have a look at the sun as an example. The core of the sun, the temperature is about 16 million Kelvin. The pressure is some ridiculous number, 200 billion atmospheres, or possibly 2 billion atmospheres, I'm not sure, lots. And those conspire to mean that the pp chain is generating energy via burning the hydrogen into alpha particles. Now, this energy generation rate, to some people in here, they'll be sort of shaking their head at that because they'll think, well, hang on, the power generation in my kettle gives out about a kilowatt, several thousand times more energy than is being produced in the centre of the sun. And this leads me to one of my favourite facts about the sun that I'm going to tell you. That energy generation rate is actually significantly less than the energy that you will get from a typical compost heap. The reason I love this fact is that it really brings it home to me how big the sun is. It's a really long way away. If you look at it, it'll burn you. But it's only generating heat. This is actually about the same as a human body. But it's just so big that it's kicking out this huge amount of energy. Now, if you consider using this as a reaction for a reactor, we have to expend that much energy. We have to get to those conditions by expending energy. And the nuclear reaction has to give us that back plus some more, or else we've lost. The thermal energy of that state is very high, and actually, if you were to create some hydrogen at those conditions, you'd have to wait over 100,000 years before you broke even, because it's generating energy so slowly. So we're not going to be able to do that. And the key point is that the reason that fusion is able to happen in the universe is because it's done on a galactic scale. It's not a galactic scale, a planetary scale, let's say. Suns are really big, stars are really big, they last a long time, and so that's how you're able to get away with using the pp chain. We can't. So how are we going to do it in the laboratory? The fundamental problem with the pp chain is that first reaction. It's a chain of three. The first one is really unlikely, actually. And if you look, this plot, it's not intended to mean anything to you, but this is essentially the rate that the reaction occurs as a function of temperature. And I want you to take note of how small these numbers are. Very small is the answer. But it turns out, if we want to get past this problem, we're going to have to use a different reaction. It turns out that there are plenty around, and actually simply by using isotopes of hydrogen rather than hydrogen itself, you can get a significant gain. So these are reactions between the same curve, but for reactions between isotopes of hydrogen, the two isotopes of deuterium and tritium. And you'll notice that there's 20 orders of magnitude difference between these reaction rates. So taking that reaction rate, that 100,000 years that I quoted before, becomes less than a nanosecond. And now we can kind of imagine that if we had to create a very high energy density state, we could imagine holding it for less than a nanosecond if we need to. And that's the premise behind what we're trying to do at Livermore, and that's the reason why we think we could ever actually achieve our goals. Excuse me. There's a problem with what I've told you so far, which is that we're talking about, I'll go back a second. If you look at the scale on this plot, that's 100 million degrees Kelvin. So that's really hot. And what do we know about hot material? It radiates very fast. In fact, we know that as you increase the temperature, the emitted power will go up as a power 4 of the temperature. And so by going to high temperature and attempting to get a fast reaction rate, we lose a lot of energy from radiation. And if we try to overcome this loss simply by driving our reactor harder, using a bigger laser or whatever, we would lose. And so it becomes essential that we kind of find a way to generate plasma states that will self-heat. And the idea behind that is that when fusion reactions happen, albeit maybe quite slowly, they will happen. The energy, we need to recycle that energy and use it to heat up the plasma. So this is actually self-heating now. So in that way, we kind of just set the reaction off into this state where it self-heats, and the rest is taken care of. It just keeps on heating and keeps on generating energy until we have the amount out that we want. Written in maths, balancing this rate against that rate, you end up with a very famous equation called the Norton Criteria, which is essentially the condition for fusion gains to be more than radiation losses. Again, don't worry about the numbers here, but I'll draw your attention to what makes up this equation. That's the density, so that's the amount of stuff that you're holding. This tau is the energy confinement time. So essentially, you have some energy in your reactor. How long does it take for that energy to get lost? That's 1 over. So how long can you hold the energy for, should I say? And this is the temperature. So what it's saying is, if you want to arrange it so that your reactor is able to self-heat, you need a lot of stuff. You need it to be held for a long time, and you need it to be hot enough. And if those three numbers conspire to get you so that this inequality is true, then your reactor will self-heat. And this is the holy grail of our research, trying to arrange it with our system so that we can satisfy this criteria. Now, since this is a product, you can kind of imagine there's multiple different ways that you can make this be true. And that's a good way of understanding the different approaches to fusion that are currently under research around the world. The one that we're doing at Livermore is not the only one. There's another one that sees a lot of investment and a huge amount of research, and that's magnetic confinement fusion. So you may be kind of aware of this research. So this is in these systems they have kind of a donut-shaped reactor chamber with magnetic fields that are arranged to go around long axis, in the long direction. The idea being that when you generate fusion energy, it's constrained to spiral round and round and round. It can't move sideways. That means that the energy is trapped. And so the confinement time is very large in that situation because the energy essentially just goes round and round and round, is never lost. And by making confinement time very large, you're able to you hope that you're able to satisfy the Norton Criteria, and then your reactor will work. These systems, they're really amazing systems. It's incredible to see them, and they're kind of our competitors, if you want. They have their own multi-billion-dollar experiment, and they have their own problems, and they think that they're going to beat us, and we think that we're going to beat them. But who knows? We do something slightly different.
Jim, I would love to know where that is. One of these other programs. Do you know what that particular magnetic confinement chamber, or is that a sample one? Or
there's only a few actually. There's a couple. You can kind of classify them into research reactors and full-blown making energy reactors. You know that from a fairly straightforward classical scaling, that the bigger the reactor is, the more stable it is. And so the ones that actually generate energy are big. So that's the Jet Taurus, which is in the UK. And that one is designed to have what they call a high Q factor, so the amount of energy that comes out is supposed to be big compared to the amount of energy they put in. But there's many smaller ones that are used, don't generate energy particularly, but they're very interesting in investigating how stable these arrangements are. And so there's several in the UK. There's several in the UK, several in the US. South Korea has one. So I think South Korea's is the only one that has superconducting magnets, which is an important point because that's the only way it would work otherwise. But anyway, that one's Jet, and I used the photograph because I was mildly involved with that at one point. This isn't what we do. What we do is we take the opposite approach. Rather than making tau big, we make N big, we make density big. We do that by taking hydrogen and compressing it. So here's a typical experiment. Another amazing photograph. This was taken at the Rochester Laser in New York, the laboratory for laser energetics. This is a small piece of hydrogen that's been collapsed down to extremely high density, extremely high pressure, and as you can see, it's releasing energy. This didn't ignite, but fusion certainly happened. And you can get an idea of how extreme the conditions are. These things are all diagnostics. Don't ask me what they are because I'm a theory bum, but I'm fairly sure this is an X-ray camera. Anyway, you can see in the front of all of these diagnostics, the amount of energy that's being released is heating up the front of the diagnostic. It's ablating and emitting light itself because this is emitting so much energy in the form of X-rays. So the fundamental idea is that, you know, these big windows you can see are laser windows, and previously to this, laser beams have come in and smashed into this piece of hydrogen and compressed it down. That's what we're trying to do. This system was a precursor to the one we have at Livermore now. So our scheme is known as inertial confinement fusion, because the idea is that we give our fuel a lot of inertia inwards, and so when it starts to fuse, it still has a bit of inertia, and that's what stops it from moving. That's what provides us with the timescale to satisfy the Norton Criteria. The idea was kicked around for a long time, but it was never entirely clear how you would project the amount of energy that you need onto your fuel. That all changed in 1960 when Theodore Neumann demonstrated his first laser. This was an extremely significant piece of work in almost every way. So this is Neumann, this is his little laser, his little ruby laser. It doesn't look like much, but almost immediately the potential was noticed by researchers almost everywhere. It didn't take long for this paper. This is the seminal paper on inertial confinement fusion. This was published, 12 years later. I'm surprised by that, but in this field, papers don't necessarily get published when they first get thought of. Anyway, in this paper, you know, this is considered to be the seminal paper. They write down how to do inertial confinement fusion. And this is the scheme that we still use today. What they described is essentially the groundwork for what we do at the moment. The picture they drew was of a spherical shell. This is a cross-section of it, made of some material. We use plastic, and that's going to be filled with your hydrogen isotope fuel. So for us, that's a 50-50 mix of deuterium and tritium. And this hydrogen fuel is going to be what we compress, and that's going to be where the fusion reactions actually happen. And this is going to provide reaction mass, as you'll see in a second. You use your laser to deposit a large amount of energy on the outer surface of the capsule, which gets very hot, the pressure goes very high, and so this material blows outwards at very high velocity. Conservation of momentum then requires that what's remaining moves inwards. So this shell implodes with material streaming out of it, and you can go most of the way to describing how this works as by saying it's a spherical rocket, and the classic rocket equation applies. But because you've confined this material inside there, this is being compressed, the temperature's starting to go up. Eventually you get to the point where it stagnates, where the pressure inside of here has got so large that you can no longer compress it. And you've reached these conditions. In our experiments, these are the sorts of conditions we're looking at. 1,000 grams per cc. I've tried really hard to make that sound more impressive, because it is really impressive. You know, a cubic centimetre weighs a kilogram. 1,000 times compressed over. I can't make it sound impressive. I'm impressed. The temperature is 100 million Kelvin. So this is 10 times more extreme than the sun in both directions. So 100 times more energy density. In our experiments, this is about 30 microns in radius. Call it 50 microns in diameter. And the idea is that now this state satisfies the Norton Criteria. So any fusion energy that's generated in the core does not leave. It's captured and heats this thing up again, and you get this runaway reaction where all of your fuel gets burnt up and you generate a lot of energy. That's the picture. And the challenge is making that be true, making this satisfy the Norton Criteria. That's the challenge. So why haven't we done it yet? I mean, I've painted what looks like a fairly simple picture about, we know what to do. We've been trying for a long time. Why isn't it working? There are a couple of challenges, and I kind of alluded to them at the beginning. Confinement is essential that when we put all this energy into the center of the shell, it's confined. It can't go anywhere. And there's a couple of important points to make sure that's true. The first is that the state that you arrive at when you've arrived at the center, that state satisfies the Norton Criteria. That's important. It's also true that the energy is able will stay there. It's not able to escape, and that's not trivial. As far as the first point goes, we know that we're giving our hydrogen an amount of energy. First law of thermodynamics tells us that that energy can either be used to as heat flow or as compressive work. Turns out for us, heat flow is very bad because that changes. What it essentially does is means we can't compress the fuel as much as we want to. Compressive work is good. So we will have to work very hard in making all of our energy. This is essentially set by the laser. We can't really change that. Goes into compression and not heat flow. The result is that the way that you change this defines a kind of a path through thermodynamic space, if you want. The way that you change that is by changing the time profile of the laser energy that you put into the target. And so our laser target our laser pulse is exquisitely tuned so that we hit the target at just the right amount, but not too hard, critically not too hard. We kind of sneak up on the fuel and we don't deliver all of our energy until we've properly prepared it. And this is there's a lot of finesse in defining this, and some really amazing experiments go on to confirm that we're doing the right thing. And I'm sorry that I'm not going to be able to describe them, but perhaps if I have time at the end. So this is extremely interesting, and this, if we get this wrong, this is an almost instant failure for the implosion. And it's not clear that we do get it right. The other issue is this question of whether we can confine the energy once we're at the centre, and that's an extremely interesting hydrodynamic problem, which I'll show you with a simulation, which we love at Livermore. I'll tell you a bit more about that later. So this is a three-dimensional hydrodynamic simulation of the imploded plasma state. This is what the hotspot, or at least this is what a computer tells us, the imploded hydrogen looks like. This is a huge amount of work. These simulations are really hard. Dan Clark, who did this, works extremely hard in making these work. But anyway, that's another talk in itself. What I want to draw your attention to is this thing. The colour scale is velocity, and the red is 500 kilometers per second. So this is a jet of hydrogen being squirted out of our capsule at 500 kilometers per second. If you imagine how much kinetic energy that is, that's kinetic energy that has not been used in order to create our fusing state. That's a loss, and that will mean we don't ignite. What's happened there is, if you imagine just squeezing the stuff with your hand, there's what did I say? 100 billion, 10 to the 11 atmospheres of pressure. You're squeezing it like this. If you've got a gap between your fingers, you're going to fire the stuff out. You're not going to compress it. You're going to squirt it out, and those gaps in the fingers are very easy. You have to be really, really precise to not get those gaps. Otherwise, you end up with that. All of these problems and more conspire to what our current experiments look like, and so I'll tell you what our targets look like. Just briefly, they're exquisite things, but this is. I'll give you the potted summary. So there's our little capsule. I meant to put a scale on here. That's a millimetre across. Perfectly spherical. If it wasn't perfectly spherical, that would translate into a gap, and we would lose confinement. Inside of there is our fuel, our hydrogen. I don't know what this is made of. It's just I just grabbed it off the internet. I presume it's beryllium. Looking at it. One thing I haven't said a single word about, but is very important, is that in the actual experiments, this thing is suspended inside what we call a hologram. This is like a gold Coke can. So this is a centimetre. In the very middle is our millimetre wide capsule, and this thing plays an essential role in smoothing out our drive on the outside of that capsule. What actually happens is we shine the laser beams onto the inside of the gold, not onto the capsule. So the gold converts into X-rays, and it turns out that those X-rays are much smoother than the laser beams themselves. And so this thing is imploded by X-rays, not by laser energy. You take a factor of 10 hit in efficiency there, but it's worth it because your drive is so smooth. So this is what when we want to see if we can fuse hydrogen, these are what the targets look like, and they get put into the National Ignition Facility, our brand new facility. So I said it was a laser, but it may not look very much like one. This is one of the laser bays. There's two. It's the size of a football field. And so these are there's a little guy there for scale. Each one of these tubes is a laser beam. And this whole room is filled with laser gain medium. So when we fire the laser, the pulse bounces backwards and forwards in its tube and is amplified up to these huge powers. The symmetry of our implosion dictates that we want to have as many beams as possible. The NIF has 192. So there's 192 of these beam lines. All of them are arranged to meet in the center of our target chamber. So here's the target chamber before it was put into the building. So this is a 10-meter diameter vacuum chamber. You can see these are the laser windows. So there's 190. No, there's I think 4 beams go through each window. So whatever 192 divided by 4 is. And then there's all these ports for diagnostics and everything else. So this is before they fit it. This is what it looks like now. So that blue thing is that target chamber, and these are all bundles of laser beams being brought in from the laser bay. And diagnostics, which I'm not going to say a word about, but are really amazing, all fit on there as well. Inside of there, on the very tip of this little target positioner, is our 1 millimeter sphere of hydrogen. And that's going to take the brunt of our 2 megajoules of laser energy, delivered in a few nanoseconds. The NIF is really cool, and I can't. The truth is, actually, I'm a theorist, so I don't go in here on a regular basis. I've probably set foot in the building 4 times, but it's amazing, and I would say that for most of you, it would be very easy to get a tour. It's taxpayers' money; they're kind of obliged to let you in. So you should ask. It's cool. And you should ask before we manage it, because when we manage to get fusion, then the whole thing becomes radioactive and you don't want to go anymore. But we haven't done that yet, so it's not radioactive. It does lots of cool stuff, but not fusion just yet. One of the most amazing things it does is power the Starship Enterprise. So this is a photo from the most recent Star Trek film. There's Scotty, Captain Kirk and Scotty's little mates standing in the engine bay of the Starship Enterprise, which is the NIF target chamber. So that last scene that was apparently inside the target chamber. I was at the lab when they filmed that. I was really excited. I was very sad that I didn't get to meet Simon Pegg, but why would you want to meet me, I guess? Okay. So, where are we at the moment? I've mentioned we haven't done fusion yet. I actually personally think that we will, but just yet we haven't. And I should clarify that when I say we haven't done fusion, I mean we haven't arranged it so that we satisfy the Norton Criteria. We haven't self-heated the plasma. We always get neutrons, get fusion neutrons out. We get an appreciable yield of energy, but it hasn't reached this runaway point yet. That's the key. So to give you a little story about what I think has been really exciting in the last couple of years, this is what you can't see really. Okay. This is a good way of thinking about our data, and this is how it looked at the end of 2012, I think. So these blue dots are experimental data points. There's actually a whole load of fainter ones that you probably can't see, but I've highlighted these 4. The axes I'm using are interesting. So this rho R parameter, this is describing how well you can find the fusion energy. A large number on this axis means that when a fusion reaction happens, you can find that energy, and a low number means you don't. So we want to be up here to satisfy the Norton criteria. This axis is that's just the raw number of neutrons that come out of the implosion. You get 1 neutron for each fusion reaction, and so this is how much fusion you're doing. So again, we want to be up here on this axis. 2012, I've highlighted these 4 shots. You probably doesn't make much sense, but if I tell you what order it happened in, it might. So first shot we did was this one, middle of 2010. Pretty poor energy confinement, not a great yield. It was the first one, we weren't overly worried. In the space of a year, that was improved very significantly. Now, this is a very respectable rho R, actually. This means we're confining a decent amount of energy. The yield is not what we want it to be, but it's okay. And then slight changes to the capsule meant that we were able to improve our energy confinement significantly. This is really encouraging because actually, when they fired this shot, the laser wasn't turned up to 10 or even 11. We weren't using the full amount of energy that the laser could use. So everyone got all excited and said, right, okay, we'll crank it up to 11 and see what happens. Both of our figures of merit went down. And so you kind of scratch your head and go, well, okay, more energy, we should just compress the thing more. We should just confine the energy better, surely. Well, what actually happened is that by driving the target so hard, we switched on another process that wasn't important before. And this is a really good example of why fusion is so hard, because it's extremely non-linear. You can do something that you think is fairly simple, suddenly something else will turn on, and nature finds a way to stop the reaction from being confined. And that's probably overly dramatic. Anyway, so this is where the title of this seminar series, what physicists do. They get a result like that and they try and figure out what went wrong. And so we did, and some very clever people came up with an explanation. And not only did they do that, they came up with a new target design, specifically a new laser design, that should mitigate this problem and make it go away. And since then, that's what we've been firing. And if I put those results on the plot, we find significant improvement. So now you can't see it, but this self-heating region is from this line shaded. So by understanding this and redesigning the laser pulse, we've moved into this regime where we've now demonstrated that our capsule has been self-heated by fusion neutrons. We're very, very close to satisfying those conditions. And this has been really exciting because this is one of the main, that's a major piece of proving that NIF was worth it, is getting into that region. What we have to do now, the thing that I'm kind of glossing over is that this design will never ignite. What they did was they sacrifice, you can see from everything's moved this way, right? They've sacrificed confinement in order to control this instability. The confinement isn't good enough to ignite, to generate energy like we want to. This one, confinement was good, but this instability switched on and killed us. So where in between those two should we aim? Somewhere in there is the way forward. And that's the situation we're in now. If anyone's interested in getting the full story, I encourage you to look at this science article because it's an extremely nice example of how we understand these targets. Okay, so in the last, I reckon 10-15 minutes, what physicists do. So this is a slightly biased description. There's thousands of physicists and scientists at Livermore of almost every flavour. But I'm a theorist. I work in a group called High Energy Density Physics Theory and Modelling. So that's what I'm going to tell you about. If theory isn't your thing, then I apologise. The truth is about these experiments that although the NIF is an exquisite piece of machinery, it's extremely difficult to get information out. We can fire the laser and we can know whether fusion happened or not, but if it doesn't, it's extremely difficult to know why. The reason for that is the conditions are so ridiculously extreme. You can't just point a camera at the thing and get a meaningful answer because it's just blowing X-rays everywhere, blowing neutrons everywhere. There's bits of gold and it's a mess. That's not to say people can't, there's some exquisite diagnostics being done and some amazing work on interpreting the information. But as a theorist, figuring out what's wrong is hard. The way that we try and get around that problem is by using computer simulations. Livermore Lab has a huge effort and a very long-term effort in developing computer simulation codes that are able to supposedly predict how these targets evolve in time. And so the idea is that for every experiment we do, we use the code to try and predict what's going to happen, 1,000 times. And by understanding the code, we understand reality. And so a large portion of the work that physicists do at the lab is associated with the simulation codes. And that's true of me. I don't run the codes myself, but there's a lot of physics that goes into how the codes work, and so a lot of the physicists care about a particular piece of the puzzle, which then gets taken and put into a larger code, and that's kind of what I do. So when I say computer simulations are important, that's certainly true. And they're essential in trying to understand, first of all, what we see, what we should do, what the targets should look like. And because of that, Livermore has some pretty impressive computing facilities. This is a picture of the Sequoia computer, currently number 3 on the top 500 supercomputers in the world. So for people in the know, 20 petaflops per second peak is pretty good. 1.5 million compute cores. If you ever try and use that many, you kind of run out of ideas of what to do with them all, to be honest. Alongside that, this isn't the only computer. There's also Vulkan is number 9 on the list, I think. And then huge resources devoted to running simulation codes for these sorts of problems. And I would note that's not the only thing Livermore does, but it's what I'm talking about today. The sort of codes that I've called a multiphysics code, the aim of these things is to describe everything. You tell it what the capsule looks like, you tell it what the laser's going to do, and it simulates everything. That's the idea. That's very hard, actually. So, in reality, what it does is solve hydrodynamic equations. You tell it what's the force on this part of the capsule, what's the force on that part of the capsule, and it'll kind of flow the plasma around and tell you what it looks like after a certain amount of time. So I showed one before, here's another one. This is another simulation by my colleague Dan Clark of what the capsule actually looks like once you've finished imploding it. I mentioned that it's a huge amount of work goes into these. It's really impressive, but there's also a huge amount of physics that goes into them. For example, I put my thing first because I'm allowed to. Atomic physics is important. My particular specialty as a PhD student was how radiation and matter couple together. And so you can imagine, this thing's very hot, it's emitting Xrays, where do they go, what do they do? Those sorts of questions have to be included. That's also important in determining what the specific heat is. So, I mentioned we give energy to this stuff. What does that energy actually do? Does it compress it? Does it ionize it? Does it heat it? That's an important thing to try and get right. Plasma physics, also important. That's a kind of I don't want to say too much about that really, but this is a difficult topic in itself, let alone at 1,000 grams per cc. Very difficult. It's also true that a large portion of these capsules, for a large portion of time, are relatively cold and extremely dense. They're in situations where traditional models for these just won't work. And we have to treat them using what would normally be solid-state physics models. And some of the most exciting things that gets done at Livermore is taking traditionally condensed matter physics models and applying them to the sorts of conditions that you encounter in an ICF capsule, in a fusion capsule. Each one of these pieces of physics is a difficult problem, and you could not even conceivably solve the hydrodynamic equations, then go off and do atomic physics, and then go off and do plasma physics, and then go off and do condensed matter. So what actually happens is that this is all done elsewhere. This is done by specialists, in offline, and then put into a form that can be used by the multiphysics code quickly. This thing will probably take several months on a big computer to run. And so if this takes a second every time step, that could translate into another month of calculation time. It's just not feasible. So people like me, we're sort of torn between getting the answer right and doing it quickly. It's a very interesting thing to try and do. Unfortunately, it's also very hard. And as I've mentioned, if you model this and you get an answer and then you do an experiment and you get a different, and the experiment looks differently to how the code told you it should, this is so complicated that it's not clear how you would then decide which physics model went wrong. You know, there's 100 physics models, one of them's wrong. How do you know which one? How do you know in what way? It's extreme, you know, it's not obvious. And so one of my personal passions, I guess, you know, one of the personal things I'm really interested in doing is trying to come up with ways of looking at these, looking at the data, and extracting physics from that comparison. So, oh yeah, I forgot about this slide. Okay, this is an example of the kind of physics that gets done offline. So these simulations are from my colleague Sebastian Hamel. These are quantum molecular dynamics simulations. So what they do is they put some ions in a box, and then they solve quantum mechanically where the electrons are in those ions, and then move the ions a little bit, solve the electrons again. And so you're kind of, the idea is that you capture everything about the material by doing that. And so in these simulations, what, you know, he's got the little dots are carbon, probably the big ones are carbon and the little one hydrogen ions. And he's taken the full quantum mechanical solution for the electrons and said, okay, these carbons are bonded together, these hydrogens are bonded together. So this is solid plastic. And what he's doing is he's increasing the temperature and watching it melt. This is solid, this is liquid. And as you go along here, it's melting. This is extremely important because somewhere in our target, you know, we go from a solid plastic sphere that we're imploding to something that's 100 million degrees. When does it melt? How much energy is associated with melting it? That's an important question. And that can really mess up the implosion if we let it. This is really cool stuff, what they do here. And you know, taking this and putting it into a form that can be understood by code is another interesting problem. This is work from my PhD thesis, where what you're trying to do is the red line is an atomic physics calculation for how iron is absorbing X-rays. The point is that, you know, it's very spiky because the atomic structure of iron is very complicated, and it's difficult to represent it correctly. Coming up with ways of representing it accurately, but that are fast enough to use in a multiphysics code, is an essential problem. And so, you know, what we do in my group is often think about ways of condensing down large atomic systems and making them run fast. And so that was the topic of my PhD. But like I say, you know, so you know, someone like me does all of this theory and comes up with an answer, and you stick it in the code, and it doesn't work necessarily. How do you know? So the other part of what I'm extremely interested in at Livermore, and there's a group of us who try and do this, is coming up with you know, applying advanced statistics to the data, the kind of thing that you would be able to do at CERN, for example, or cosmology, applying it to our situation. The critical difference is that we have like 30 data points, whereas, you know, in other fields you're in quite a data-rich environment where extremely data sparse. So coming up with ways of performing statistical inference in those data sparse environments is extremely important for us, and relies on a combination of stripping down the physical models, you know, hopefully retaining the physics, but meaning that we can run them and sample them 1 million times as opposed to 4. Combining that with, you know, proper treatment of the statistics is important. So this is an example. So this is what you might want to know is, you know, okay, what if my radiation model's wrong? What's the probability that that's changing our answer the way that we see? And so this is a stab at trying to do that. Essentially telling you how the output of one of our diagnostics varies as you change the physics models. And this is kind of the inverse problem, looking at the data and using it to infer what should be wrong, what could be wrong with our physical models. I'll draw your attention to the preliminary labels on these plots. The truth is that this is based on a physical model that we are still working on. This plot probably changes on an hourly timescale, so don't read anything into it. Okay, so I'm just about done. I'll leave you with this plot, which is supposed to be a fair representation of what physicists do, who at Lawrence Livermore Lab involved in ICF research. I've talked about theory and models a little bit. That's what I do. I've also talked about the experiments, or at least how they work, and the multiphysics modelling. But alongside that, there's a huge amount of focused experiments that get done on the NIF and on other experimental platforms. This is the Z machine at Sandia, which is also really cool. You should look it up. This is the Titan laser, which is at Livermore. This is that same laser that I was talking about, the Omega laser at Rochester. Really exquisite experiments in extremely hard, extremely difficult conditions to get us information, which then gets fed to the modelers to see whether that is consistent with what we think. Diagnosticians designing X-ray cameras with picosecond time resolution to image our collapsing capsules, and all sorts of amazing things get done in this bubble that I haven't talked about or understand. And of course, it's all linked together. It's not like we all sit in a building and talk about theory and nothing else. It's a really, really exciting thing to do to be involved in this, how all this feeds back. Okay, so with that, I'll finish.
Wonderful presentation. Thank you for giving us time. We're going to have questions from now till 5, and then there might be some more questions after that. But we'll let some people go if they have other things to go to. But let's start off with some questions. Yeah, John.
I'm just an experimentalist, but the high density to start with would presumably mean low temperatures of the liquid, below 20 Kelvin.
You mean the initial state of the capsule?
The initial state.
Right.
But the whole around, is it room temperature?
So
and that
the hologram is not cooled.
not cool.
The whole chamber is under a vacuum, so it's not room temperature.
No.
But the critical thing that I left out of my talk is that actually what our targets look like is, there's the plastic shell I talked about, there's the gas fill I talked about. We freeze a layer of hydrogen on the inside of the plastic, and the idea is that actually, if you implode this thing, the density that it reaches at the end is simply related to the density it started at. We aim for an adiabatic implosion. Whether we get one or not, well, we don't get one, but anyway.
What you hope for.
And so, when fusion happens in the hot stuff, this ice is what captures the alpha particle. This is what captures the energy. And so what you're hoping for is that the hot stuff in the inside launches a burn wave through the ice. And so ignition is the point where we reach conditions here that are hot enough to burn all of the ice. So we purposefully arrange it so we have a very high density, 1,000 grams per cc, and a very hot 100 million Kelvin. They weren't, there's not a place in the capsule where it's both 100,000 grams per cc and 100 million Kelvin.
Thank you.
Yep.
You mentioned that you convert the UV pulse to an X-ray pulse. Is that pulse just a thermal conversion or something else involved?
Yeah, we're aiming for thermal Planckian
So you
X-ray
just
spectrum.
get something hot in the inside of the whole room, and that re-emits X-rays.
Right. The idea is that the whole run's made of gold, and so you launch a thermal wave into the gold. Behind that thermal wave, you've got something like I'm not going to be able to do the unit conversion. 300 electron volts behind it, and that's emitting thermally. And so what we see, what drives the capsule is a 300 eV Planckian. with an extra little bit, which is very high energy X-rays from the atomic structure of the gold. And that's a very critical part of the problem, because those can go straight through the capsule and melt the ice. And so mitigating that is an important design consideration of the capsule.
Thank you. Just worry about the effects of neutron bombardment from your action on your equipment.
Well, I mean, I can't answer that completely. I mean, we don't. If we ever ignite, then the target area becomes unsafe because the neutron flux is so high. Now, I can't answer the question about whether the diagnostics we use will be broken by that. I have to suspect not. The target chamber being 10 meters diameter, everything stood off so far away that I don't think that would be a problem. Actually, the biggest problem, as I understand it, is not so much the neutrons; it's the debris. I had a plot of it. Oops. So the actual package that we fire looks a little bit like this. So this is end on, right? So the can is into the board. You can see that this is the capsule. And it's surrounded by all of this. This is all thermal packaging that's associated with freezing the hydrogen on the inside surface. So all of this just explodes. And it bombards everything that's at the outside of the chamber with stuff. And that's a major consideration. That can really do damage. And one of the driving factors on what experiments we do is, if we do a full-blown, crank it up to 11 shot, then that will do significant damage to the final optics of the laser, and so we can't do it that much. Sorry.
Was 500 terawatts of power?
Yeah.
Less than 10 seconds for these lasers?
10 nanoseconds. Yeah.
Okay, I was wondering about your guys' utility.
Well, so we fire about once a day at those powers, less than once a day. So when I had my job interview at Livermore, I had a tour, and someone very flippantly said that it was just plugged into the wall, and you just charge. That's not very much energy actually, and so it has huge capacitor banks that are involved in delivering that energy when you need it, but the amount of energy isn't all that big, and so, I mean, I can tell you that the power bill for the supercomputers will be a lot worse than it is for the laser. Okay.
So at one point you mentioned that when you guys turned up the power after those first couple of experiments, that you had some problems due to some unexpected effect in this. Can you elaborate on that?
Sure. Yeah. One of the major problems that we have to worry about is the Rayleigh-Taylor instability. So that's this thing. That's a simulation of what I'm talking about. What happens is that if you take a heavy fluid and push against a light fluid, you get these kind of structures forming, and it's there's all sorts of cool stuff that this happens in ambient conditions. It's interesting, but there are two parts of the implosion where that's true, and what's happening is that this is relatively cold, this is relatively hot, and so you're shooting cold material into what you want to be hot, and it will cool it down. And so, if this happens to any significant degree, all of your energy is involved in heating this stuff up, and it's a form of energy confinement loss.
So you created too much of an energy gradient and that happened.
Exactly. Yeah. Interestingly, so there's an analog in the sun, which is where in the sun the energy is generated in the core and propagates outwards. At some point in the atmosphere, the energy gradient gets really high, and convection happens because the energy gradient is too high, and nature finds a way of evening it out. And that was what my PhD was in to begin with.
Thank you.
There's a question over there somewhere. Yep.
Back on the target there, so these Rayleigh-Taylor flow instabilities,
Yep.
that you were talking about. I mean, the one with the hole up, or the ice gel one.
Oh yeah, yeah, okay.
So coupling the X's, backing up, the 355 nanometer radiation hits the holon. The
Okay.
holon generates the X-rays
Right.
to intersect in the shell.
Hmm.
The shell is frozen in the middle, and you want to boil from the inside out and keep that skin to hold it together. Is that right?
Yeah, so I mentioned that we don't want
You
to
don't want the
heat, we want to put our energy into PDV work, not into compression, not into entropy, essentially. So if we were boiling the fuel, we would be worried by that. What we want is for this thing to just compress.
and not squirt out.
Right,
And the Rayleigh-Taylor instabilities you're talking about are the interaction of the plasma with the X-rays trying to get in and the plasma trying to get out.
yeah, I mean, it's the Rayleigh-Taylor instability just happens when you're when you have an interface between two different densities that's too sharp, essentially.
And so this is in the thermodynamic domain or the plasma photon interaction?
The thermodynamic domain.
So why not use something with more inertia?
Good question. That's actually one of the things that we're exploring. The advanced designs that are kicked about all involve different materials other than plastic. And there's high density carbon is proposed, beryllium is proposed, and that's the balance between how fast it explodes when you deposit energy, because that's your rocket drive, and also the kind of specific inertia that it has on it. Yeah, right. But
You had a diagram to show the density versus the speed as a function of the location. So in reality, do you really have an array of sensors to measure the two parameters to validate your model, or?
that's very difficult. So you're talking about the kind of this kind of plot.
Right. How do you really? I mean, I'm still not exactly sure how I'm going to use the model to validate or the data to validate the model, because it really involves so many parameters. And,
Right.
if you change one of them, you can really see something completely different.
You're preaching to the converted. I completely agree with you. The situation is, this is the hot material. It's surrounded by 1,000 grams per cc plastic. There's no appreciable signal getting out of here, and what does get out of here has been scattered so much. Huh?
The neutron flux?
The neutron flux is a really good one, and that's actually really interesting. The angular distribution of the neutrons and things like that is a really useful diagnostic. But the truth is that we have to look at extremely integrated quantities. We have to look at the time-integrated neutron flux and things like that contains information, but not simply related to this. So the truth is, we kind of have to be clever about the way we think about these simulations and be careful about what we infer from them. It's hard. You can't just probe this stuff. This is happening completely, behind a closed door.
Let's thank Dr. Gaffney again.